There is a bacterium living in ordinary soil right now that turns loose sand into solid stone. No heat, no kiln, no cement, no carbon dioxide. You pour the sand into a mold, introduce the bacteria, wait 72 hours, and what comes out is limestone. The same mineral that built the pyramids, the Colosseum, and every great cathedral in Europe. The same mineral in seashells. The same mineral in your bones. This bacterium has been doing this since before the dinosaurs existed. The science is not theoretical. The production is not experimental. The powder exists in a bag that a contractor can open on a job site, add water, and deploy within 24 hours. So why have you never heard of it? And why, in 2025, do the building codes that govern every construction project on Earth still refuse to recognize it? That is exactly what we are going to find out. Sporosarsina pasteurei is not a new discovery. Microbiologists first cataloged it in the early 1900s, finding it in soil, in caves, in lake sediments, on the ocean floor. It was a curiosity, a footnote in microbiology textbooks. A bacterium that did something chemically interesting in a petri dish and nothing obviously useful anywhere else. What made it interesting was a single enzyme it produces in extraordinary quantities: urease. Urease breaks down urea, a nitrogen compound found naturally in soil, and releases carbonate ions into the surrounding solution. When calcium is present, those carbonate ions bind to it and form solid calcium carbonate crystals, limestone. The bacteria had been doing this in soil for hundreds of millions of years. Nobody had thought to ask what it could do on a construction site. In the 1990s, a soil engineer named Jason de Jong at the University of California, Davis started asking exactly that. He was trying to stabilize loose sand in earthquake zones without chemical grouts that poison groundwater and require energy-intensive manufacturing. He injected the bacteria into a column of sand like a doctor administering medication, not to kill anything, to build something. The sand was hardened. By the time de Jong published his results, the United States Army was already paying attention. The military had a specific and urgent problem in Iraq and Afghanistan. Helicopter landing zones built on loose desert sand generated choking clouds of dust and fine particulate that destroyed turbine engines, grounded aircraft, and blinded pilots during approach. Chemical suppressants existed. They worked for a few weeks, contaminated the soil beneath them, and required constant resupply across active combat logistics chains. De Jong's bacteria offered something different, a treatment that stabilized the sand by growing stone inside it. DARPA funded the research. Field trials were conducted in desert conditions, in heat exceeding 130 degrees Fahrenheit. The bacteria worked outside the laboratory exactly as they had worked inside it. The landing zone hardened. The dust clouds stopped. No press release followed. No announcement. No technology transfer ceremony. The military uses what works, documents what works, and moves on. What is remarkable is not that the Army tested it. What is remarkable is that the construction industry, watching the same results, did not. To understand why the bacteria work, you have to understand what they are actually doing inside the sand. Urease breaks down urea and releases carbonate ions into the surrounding solution. When calcium is present, those ions bind to it and form calcium carbonate crystals. But the chemistry alone does not explain the structural result. The critical detail is where the crystals form. Sporosarsina pasteurei has a cell wall that carries an exceptionally strong negative charge. Calcium ions carry a positive charge. The bacterium attracts calcium the way a magnet attracts iron filings. The cell itself becomes a nucleation site, a seed crystal. Limestone grows directly around it, encasing the living bacterium inside the stone it produced. Think of it as mortar between bricks, except the mortar is grown, not mixed, and the bricks are individual grains of sand. Crystal by crystal, contact by contact, the loose material that poured through your fingers becomes a load-bearing solid. Laboratory columns at UC Davis have achieved compressive strengths exceeding 10 megapascals, comparable to soft sandstone, sufficient for ground stabilization, foundation improvement, and erosion control, achieved without a single degree of added heat. The person who took this out of the geotechnical laboratory and into architecture was not a soil engineer. She was an architect named Ginger Dozier, who grew up collecting seashells on a beach in Alabama. In 2006, she was working in the United Arab Emirates, watching concrete being mixed by the thousands of tons on every block around her, and she started thinking about calcium carbonate. A seashell is calcium carbonate. It is harder than most ceramics. It is grown by a living organism at sea temperature, without heat, without fossil fuels, without a kiln. She found the literature on microbial-induced calcite precipitation. She found Sporosarcina pasteuri. Then she ran 111 experiments that failed. The 112th worked. She packed sand into a rectangular mold, introduced the bacteria, added calcium and urea, and waited 5 days. She removed the mold. The brick held its shape. Compressive strength comparable to fired clay brick. Produced at room temperature. Zero carbon dioxide. In 2012, she founded Biomason in Raleigh, North Carolina. Their first commercial product, a tile called BioLith, is in real buildings right now. The United States Department of Defense has contracted Biomason to develop marine biocement that sources nutrients directly from seawater and repairs itself underwater. Her stated goal is to eliminate 25% of global concrete industry carbon emissions by 2030. The production is already running. Cement production accounts for 8% of global carbon dioxide emissions, more than aviation, more than shipping. 4 billion tons manufactured every year. A bacterium that produces zero emissions, runs at room temperature, and ships as a dry powder should be the most discussed material in construction. It is not. The reason is not conspiracy. It is 3 separate walls standing between the laboratory and the job site. The first wall is ammonia. Urea breakdown produces ammonia as a byproduct. At construction scale, unmanaged ammonia release is toxic to aquatic ecosystems. Researchers are working on zeolite absorption and process redesign that reduces ammonia output by up to 75%. The problem is real, and it is not solved yet. The second wall is cost. Portland cement costs roughly $100 per ton. Biocement production costs are significantly higher because the bacterial growth media, the urea, and the calcium chloride all carry input costs that limestone and heat do not. The cost curve is moving downward. It has not reached parity. The third wall is the building code. There are no ASTM standards for microbially induced calcite precipitation treated soil or biocemented aggregate. An engineer who specifies biocement today is writing in a language the code does not recognize. The insurer will not cover it. The contractor will not risk it. The default is Portland cement, every single time. The cement industry does not need to suppress biocement. It simply needs to wait. That is exactly what it is doing. The bacteria do not care about building codes. They have been turning sand into stone for hundreds of millions of years, long before the first human mixed the first batch of mortar, long before the first kiln was fired, long before Portland cement existed as a concept. The science is done. The production is running. The powder is in the field. For the highest load applications, skyscraper cores, and major bridges, Portland cement will hold its position. For ground stabilization, erosion control, marine structures, and low-carbon construction, Biocement is not a future technology. It is a present one being held at the door by paperwork. The bacteria will still be building long after the last kiln goes cold.